Hello everyone. So in today's video lecture, we're going to be talking about electron configuration. And electron configuration basically just means the arrangement of electrons going out from the nucleus. Recall that in the previous lecture, we talked about the nucleus, which contains the protons and neutrons, and the huge electron cloud, which consists of orbitals, which actually have electrons in them. Okay? There are two diagrams that's shown in you, and this diagram here, you're actually showing you the Bohr model. And the Bohr model shows you the nucleus, and then in this case, the shells going out from the nucleus. Note that there's a first energy level, the second energy level, the third energy level, fourth, fifth, sixth, and seventh energy levels actually in the Bohr model. Now, the 7 energy levels coincides actually with the period, okay? The period of the periodic table. So the period, folks, just tells you the row. So this is the first period. Lithium, beryllium all the way to neon is the second period. Sodium all the way to argon is the third period. Potassium all the way to krypton is the fourth period, so on and so forth. Okay? Groups, we call groups this columns here. So hydrogen to francium is group 1, beryllium to radium in this case is group 2. Okay, so periods coincide again with the energy levels. So I'm going to go back to this thing here. All right, so this is one way. Now there are actually maximum number of electrons that can occupy its period. So in the first energy level or the first period, you can only have 2 electrons. Okay. In the second energy level or the second period, you can only have 8. Okay, I'm sorry again, because of this is cursor. Third, 18, and then you have 32 in the fourth energy level. Okay, and there's actually a way that you can calculate this, and that is that mathematical formula is 2n squared. So if we want to calculate the maximum number of electrons that the 7th energy level can actually occupy, we will then write 2. All right, I'm going to put a parenthesis here, 7 squared. 7 times 7 is 49. Okay, that's a squared symbol. And 49 times 2, folks, is 98. All right. So you actually can have a maximum number of 98 electrons, right, in the 7th energy level. So that's actually how you calculate how many electrons can actually fit into each shell. Again, the shell, the period, and the energy level are the same. Okay, so that's actually how you can deduce those numbers. On here, there's actually a different diagram, and this is actually the orbital diagram that you can actually do. And the reason why it's called orbital diagram, folks, is if you look closely in the orbital diagram, you actually see boxes. Boxes. Okay? Each box is actually an orbital. All right? And each box or each orbital can actually contain 2 electrons. So each box contains 2 electrons. Note that there are letters now. So there's an S subshell in this case. You have P subshell, D subshell, F subshell. Okay. If you look at the S's, each S subshell only has 1 orbital or 1 box. So each S subshell can contain a maximum of 2 electrons. The P subshell, if you look at it, it consists of 3 boxes. Since each box can contain 2 electrons, the P subshell then can contain 6 electrons. If you look at the D, 5 boxes or 5 orbitals, so that can contain 10 electrons. F, 7, so that can contain 14 electrons. Okay? I hope that's... Now, if you look at these boxes, this is 1 box, 2 electrons, 3 boxes, 6 electrons, D, 10 electrons, F, 14 electrons. If you compare that, folks, to the table of elements. I don't know if you can see this, but hydrogen and the beryllium group has 2 boxes. I should say 2 boxes, but 2 electrons. Okay, so this is actually the S subshell. If you look at from number 3 to 12, 3 to 12, folks, is 10. Guess what that is? That is the D subshell. If you look from boron to neon, that's 6. Guess what that is? Those are the P subshell. And if you look at the lanthanoids and actinoids down here, 57 to 71 and 89 to 103, they have 14 boxes coinciding with electrons, which is the F orbital. So it's not a coincidence, all right, that actually the table of elements is created thus. Okay, so we're going to go back here. So what is the reason why you need to understand this filling here? One of the things is, in this class, I'm going to ask you to do electron configuration. And I can ask electron configuration based on any of these models plus one more, which we're going to cover later, here or here. So let's do an example. So I'm going to just pick an element, a neutral element. So let's say I am going to, let's say, pick, maybe I should erase this, guys. All right, so to be cleaner. Let's say we're going to pick a neutral atom of iron, iron 26. Okay, so iron, folks, 26 protons. If it's neutral, if this is neutral, that means to say that number of protons is also the same number of electrons. So therefore, if it has 26 protons, it must have 26 electrons. So we need to, in this case, assign the electrons to energy levels or in an orbital diagram as thus. So we have 26 electrons. So what is the maximum number again that first energy level can contain? It's 2. So we can put 2 in the first energy level. Second energy level, we can have 8. 8 plus 2 equals 10, right? I hope you guys are counting because I don't think I am. So now, hypothetically here, I could have 18 electrons. Okay, folks. However, I only need a space for 26 electrons. So therefore, I should write this. I can only, for iron, the arrangement is 2 in the first energy level, 8 in the second energy level, and 16 in the third energy level. Okay, so that's one way we can actually, in this case, symbolize the number of electrons in electron configuration. Now, I can also ask you to do it this way. So again, first energy level, again, remember each box can contain how many again? 2 electrons. So in the first energy level, I'm gonna go 1. Folks, I'm sorry, this is very difficult for me. Okay, cursor. So there's 2 electrons. That takes care of that. Now look at this one. The way you fill this, folks, is you fill it from the bottom up. So then 2 is next. Okay, up, down. Those are just the directions. And now, folks, we cannot do S because P is closer to the bottom. So we're gonna do P first. We're gonna go 1. Folks, I'm just gonna try to rush here. Okay, please remember that all of these hash marks just means to say that they have opposite spins. So that contains 2, 4, 6. Next one is 3s. I'm not even drawing the hooks right now, okay, because I'm just lazy. So 2, 4, 6. So that's 10, 11, 12, 13, 14. I'm going to do it properly. 15. You're actually supposed to go each box first before you go back, right? I lost track already. So again, 4 plus 6 is 10. 10 plus 2 is 12. 12 plus 6 is 18. Okay. 18, 19, 20. Now, folks, here we go. Which one is closer to the bottom? This subshell here is closer to the bottom. We fill it first. So now again, 10 plus 18, this is 20, so I need 6, okay? So I'm going to go 1, 2, 3, 4, 5, okay, 6. I hope I'm right there. So let's see again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, so there are 26 electrons. So there's, again, many, many ways. My apologies again for not being able to like throw this up and down here, but that is the way this is going. Okay, so again, so there's two ways. This way or this way. But they're the same. It just represents how electrons actually, in this case, occupy energy levels outside of the nucleus. All right. Imagine that, like if you go to a theater or like a movies, you have the screen and then you actually have seats, right, in rows behind it. This is basically what this is. Electron configuration is just the seating arrangement for electrons. Okay. So this is one way that you can do this. Now, the other way that you guys can do this electron configuration, folks, is by using this technique here. 1s2, 2s2, 2p. And again, please remember, this is a diagonal slash here. So you go 1s, then 2s, then 2p, 3s, then 3p, then 4s, then 3d, then 4p. Follow the arrows. And the most important thing that you have to do is remember that all s's can contain 2, all p's can contain 6, all d's can contain 10, and all F's can contain 14. All right. So if I'm going to do iron in this case, 26 again, still the same. Nothing has changed. All right. 26 electrons. I'm sorry, guys, this is going on forever. And because, again, I'm using a cursor, I'm just going to, you do 1s first. So the way I do this is to go 1s, and then you put 2. The exponent basically, or the subscript basically just tells you how many electrons there are. Then guess what's next? It's 2s, 2. After 2s2, it's 2p6. It's taking too long. After 2p6, folks, it's 3s2. After 3s2, it's 3p6. All right. After 3p6, there's 4s2. I'm going to draw it down here. And after 4s2, this is the thing here. After 4s2, folks, we loop around. We go back to 3d. And we go 3d6. And why did I do 6? Again, count 2, 4, 10, 12, 18, 20, 26. Now, note here that this notation is the same as this notation that I've done previously, okay? The only difference is this is longer and you have to do a lot of hash marks, and in the other case, it's a little bit shorter, okay? So that is actually how that configuration actually occurs. Now in this configuration, there are actually two different sets of electrons. And what we're going to do is might as well just jump away. We have what we call core electrons, or electrons in the middle. And we have valence electrons. And those valence electrons are electrons on the outermost period, the outermost shell, or the outermost energy level. And folks, valence, the way you do this is you actually look for valence electrons. So what I'm going to do in order for you to find valence electrons is you look at the highest number in front of any letter. And the highest number among all of these things is 4. All right? And so valence electrons, there's only one 4. Now, if there were 2 4s, you would consider them both. But since there's only one 4, we're only going to consider this. And in this case, if you look at the number on top, we actually have 2 valence electrons. 26 minus 2, folks, is we have 24 core electrons. Okay? So that's actually how you can deduce core versus valence electrons. So again, very quickly, as an aside, there are 3 ways that you can represent electron configuration. You can do the Bohr model, which looks like the planetary model. Actually, it's called the planetary model. You can actually do the orbital diagram. And then this is the full notation, as we call them. All right?